Good morning, everyone. Today we will start with the next type of transform, discrete Fourier transform. Okay. So in our last class, if you see, we were discussing about DTFT. So in DTFT, if you see, as we discussed in our last class, that it is meant for the discrete time signals. Right? Now we get the discrete time signals. So as we know that the discrete time signals, they are discrete in time. So they vary in 0, 1, 2, 3 till infinity it goes, and again you may have it in the negative half also. So amplitude versus time, discrete time. Okay, but when we perform, when we come to this frequency axis, this frequency component, it is basically a continuous signal. Okay, the frequency domain plot, it is a continuous signal, and accordingly when we perform this IDTFT, inverse discrete time Fourier transform, we have to implement integral, right? So we can see over here in the integral, uh, we need to process the, basically we need to process the continuous signal. Okay, so over here if you see, initially we had discrete time signal, then in after we do the DTFT, we get this frequency domain signal omega versus amplitude, and over here we will be getting some continuous profile. So we have got this continuous profile. If we apply IDTFT, since this what do you call, the Fourier transform domain, it is continuous in nature, during the implementation of the IDTFT we have to implement the we have to employ integral calculus. Okay, so we also discussed that due to this reason these systems cannot be implemented in the computer, which are mainly meant to handle discrete time or discrete signals in general. So this is one of the disadvantage of the DTFT and IDTFT transformation pair. So how we can overcome this problem? We can overcome this problem if we sample this frequency spectrum. Okay, so we can say sampling. So if we perform sampling of this frequency spectrum, then we can make this frequency spectrum a discrete one, and we can then perform the inverse transform in a way such that it can be computed using a computer. With this logic, the discrete the discrete Fourier transform, it has been proposed. So if you see over here, it's written in the same thing. To do processing in a computer, it is essential that the quantities involved be discrete. Okay, a sample time signal satisfies this requirement. However, its Fourier transform does not satisfy this criteria. Hence, its Fourier transform should be sampled. Okay. Herein, we are basically talking about the DTFT, IDTFT transformation pair. Okay. Now there, over here, we have written a lot of. I have written a lot of things. So rather than discussing this in the text form, let's first discuss. Let's first see this chart. I have taken this chart from one of the websites, but however, I am not able to locate that website again, so I am not able to give the due credit. But whosoever has made this chart, he has summarized why we want to do the DTFT. Sorry, no, why we want to do the DFT. Okay, so we all know that we have, for a particular signal, we can analyze the signal in the time domain and the frequency domain. Okay. Now, in the time domain, we have the normal signal, say x of t. Okay. So, for that particular signal, we will be having x of omega. Okay. That's fine. Now, to make this signal discrete, what we need? I have previously talked to you that if we want to discretize any signal, we need to multiply with an impulse train. Right? So, this is the impulse train. Now, it is interesting to note that the Fourier transform of a discrete time of an impulse train is also an impulse train over here. If you see, at frequency equal to 0, we have an impulse, and then at particular periodic points we have these impulses which are repeating itself. Now, for discretizing, what we need to do? We need to multiply xt with delta t. Okay. So we will be getting, for getting xn, we need to multiply xt multiplied by delta t. Right. Now, when you do this, we get the discretized signal. Okay. Now, yesterday we have talked about one property, that multiplication in the time domain, it is convolution in the frequency domain, and vice versa. Okay. So in this case, we have multiplied in the time domain, whereas in the frequency domain it would become the convolution. So when we do the convolution over here, so what is happening basically? Basically, if you look into the signal and if you compare it with A, if you compare A and C, in A we had a spectrum which is non-periodic, or we can say aperiodic. Okay. Now, when we have convoluted the aperiodic signal with the impulse train in the frequency domain, the signal has become periodic in nature. Now, due to this property, what happens is that we have a property called Nyquist property, which needs to be employed before we are sampling any time domain signal. Why what does this Nyquist property helps us to do? So Nyquist property tells us that when we have to sample any signal, so fs should always be greater than equal to 2 of fm. Okay. Now, how do we ensure this fm? In one of my previous class, I have told you that we can ensure the fm by band limiting the signal. We can ensure fm by band limiting the signal. Okay. So if you see, band limiting means we are restricting the frequency components of the signal. So if you see, if we perform sampling in the time domain, we are band limiting or restricting the frequency components in the frequency domain. Okay. Now, why we want to do this? Because when you talk about these discrete time signals, they can acquire values in the range of 0 to 2 pi. So your frequency components, they are same. Okay. And after every 2 pi, the signal components, they will repeat itself. Okay. So when there is a periodic signal, that means you can say 0 to 2 pi or minus pi to pi. The frequency component will vary in the range of 0 to 2 pi or minus pi to pi. Okay. So due to this reason, what is happening is that if you see this red shaded area in C, this is the original one. However, the blue shaded area, they are the repeated components of the same frequency components, which has been shaded in red. Okay. So if we do not band limit the signal, then what will happen? There might be a small area in between, which I am shading in black, wherein the frequency components between the two repeating peaks, they will be mingling with each other. So if you see, the herein in the main lobe we will be having the higher frequency component, but in the repeating lobe it will be having the low frequency component. So the low frequency component will mingle with high frequency components. Okay. And due to this mingling of the low frequency component with the high frequency component, we will be having a distorted signal, and that is detrimental to the signal reconstruction. Okay. And this intermingling of the low frequency component with the high frequency component is called aliasing. Okay. Now you have to remember what we have talked now. We have talked that when we have done sampling in the time domain, we have band limited the signal in the frequency domain. Now what we have proposed just before, we have proposed that we need to sample the frequency component or frequency spectrum, right? For getting DFT or a transform which can be implemented in a computer, we need to sample the frequency spectrum. Now, if we have to sample this frequency spectrum, then what we have to do? By the previous stage analogy, suppose this is the stage 1 where we have sampled in the time domain, we have band limited the signal in the frequency domain. So now we want to sample the frequency spectrum. So we have to now time limit the signal in the time domain. Okay. So this is what we need. Now, what is time limiting? Time limiting means we need to restrict, or we need to take only a specific portion of the signal. Now, when we want to take the specific portion of the signal, we multiply the signal with a rectangular pulse. The reason being, the rectangular pulse, it is present within a particular period of time, and at other instances it does not have any value, so it is having an amplitude of 0. So when you multiply it with the signal component, so only in the time period where the amplitude of the rectangular pulse is 1, you will be getting the frequency components value, and signal components value, and at other time instances you will not have any amplitude value. So that means you are limiting the signal within a specific period of time. And when we have a rectangular function, and if we perform the Fourier transform of that rectangular function, we basically get this kind of curve, which is called sinc function. Okay. Now again, in the time domain we have multiplied, so in the frequency domain it will be convolution. So after multiplying, we get this signal, which is time limited signal. So we get time limited signal. Okay. And then if you go for this Fourier transform, you get that with some distortion, because you are convoluting it with the sinc function, with some distortion you get the frequency spectrum. Now once you get this frequency spectrum, now this time limited the frequency spectrum of the time limited signal, it is ready to be sampled. Okay. Same thing, we need to multiply it with an impulse train, but this time we have to multiply in the frequency domain. So delta t, f or omega, whatever you can use. So previously I think we have used x of omega, so here also we can use omega. Okay. So delta t omega. So if you perform multiplication over here, it becomes convolution in the time domain, and then when you multiply it, you can see we are getting a discrete discrete frequency spectrum. Okay. And when you are convoluting it with the impulse spectrum in the time domain, you can see the signal components, they are repeating itself after the initial time period what we have for the window what we have selected. Okay, so herein in the last step, if you see, both the time domain and the frequency domain signals, they are discrete, and both of them, they are periodic in nature. Okay, both of them, they are periodic in nature, discrete and periodic in nature. Okay, so this is the essence of discrete Fourier transform. Okay, in the discrete Fourier transform, both the time domain signal and the frequency domain signal, they are discrete in nature, and due to this reason, both the forward transform and the backward transform, they are they can be processed in a computer, which was not possible in no, what you call discrete time Fourier transform, inverse discrete time Fourier transform pairs. Okay, the reverse was not possible over there. Now let's look into this whatever we have discussed. Now look into this what you call this text, what is written over here. The sampling in the frequency domain is achieved by multiplying by an impulse train, okay, delta t omega, similar to the time domain sampling, okay, with its period decided by the signal duration in the time domain. Let's forget this. The main essence is we are sampling the frequency domain component with an impulse train by multiplying it with an impulse train in the frequency domain. Okay, so the IFT, inverse Fourier transform of this impulse train, is another impulse train delta t. Further, multiplication of delta t omega and x of omega s gives x of k delta omega s in the frequency domain. That means we have now discretized the frequency component. Okay, this results in a convolution of the sample time signal x of nts and the impulse train delta t in time, resulting in xn nts, which is periodic in nature. Okay, to recover the time sample signal, the frequency sampling should avoid possible time domain aliasing. Okay, that means the signal length decides the frequency sampling rate. Okay, so yeah, I forgot to tell this one. So this is an important thing. The signal length decides the frequency sampling rate. In the Nyquist property, what you have said, the maximum frequency within the signal, it will be affecting the at what frequency we will be sampling. Similarly, the time length we are of a signal whatever we are taking, that would affect the this sampling frequency. Okay, so the frequency sampling rate, right? Such a FT involves sampling both in time and frequency, is called discrete Fourier transform, DFT. In a DFT, the periodicity is built in both time and frequency due to the sampling, though the original signal may not be periodic in nature. Okay, so even if you see over here, we have started with an aperiodic signal, but we have ended with a signal component which is periodic in nature. So even if a signal is aperiodic in nature, we will always get a signal component, time domain signal component, which is periodic in nature. So the analysis of the DFT, it is bit tricky, and it requires some what you call some expertise to analyze the discrete Fourier times signal. Otherwise, if no one knows, then what will happen? you will be you may be analyzing the extra time component signal as a what do you call, as a periodic signal, and your analysis may be wrong. Okay, so this is there. Any questions till now? Is it clear to all of you, or do you have any questions on this? Hello, is anyone there?
Yes, sir.
Yes, sir.
Yeah, so do you guys have any
Yes, sir.
question? You tell something. All of you are keeping mum. Okay, anyway. Now, if you look into the DFT, which is the forward transform, xk, it is regarded as the frequency spectrum component. It is given by summation of n equals to 0 to n minus 1 xn w n kn, where this capital N, it is the length of the signal. Okay, and it varies from 0 to n minus 1. Okay, similarly, this k value, it also varies from 0 to n minus 1, and this n values also varies from 0 to n minus 1. Okay, then in the IDTFT, it is x of n 1 by n summation of n equals to 0 to n minus 1 xk w of minus kn n. Okay, so if you see in the forward transform and the inverse transform, we have a factor w n, and there may be this kn or minus of kn. Okay, so basically these two are the conjugates of each other. Okay, and this w n kn, it is regarded as the Twiddle factor. So it is regarded as the Twiddle factor, and wkn, if you have this one, so that means it goes minus j 2 pi by n multiplied by kn. It becomes multiplier on the what do you call with this factor 2 pi by n multiplied by kn. Okay. Now, suppose we have a signal xn, so we get this signal xn, then if you see what we have done, we have said that n equals to n equals to 0 to n minus 1, we have xn multiplied by the Twiddle factor in the forward transform. So xn, if we use the matrix multiplication method, then we have xn wn multiplied by xn, that means the signal input. So we have this Twiddle factor wn, uh, then we have this Twiddle factor. So I will come to this how we can make this. So it is just the simple matrix multiplication between the Twiddle factor matrix and the input signal, and and for the xn, that means the inverse Fourier transform, we have 1 by n multiplied by Twiddle factor conjugate multiplied by xn, which is the frequency components values. Okay, so if you see over here, you have to remember that we have a multiplication of k and n. So how do we get it? So n equals to 0, sorry, not 0. For n equals to, so we will be having 0, 1, 2, 3, so on to say n, capital N. Okay, because we are going for n by n matrix. What is n? N is the length of the signal. So n is the length of the signal 2n. Similarly, k will vary from 0, 1, 2, 3 and so on to n. So if you see this first column and first row, it will always be wn0, wn0 and so on. Okay. Similarly, first column also we will be having w0. Then you have 1 multiplied by 1. So this is see wn, w1n, then 2 multiplied by 1, w2n and so on. Similarly, over here also you will be getting the same thing. So w00, so you will be having w0n, w1 multiplied by 2, w2n, 2 multiplied by 2, 4, so w4n and so on. Similarly, we will be having in the third column and also the nth column. Okay, so why, what is the value of wn0? The wn0, if you look over here, if your kn value is 0, it makes this superscript as superscript as 0. So we get e to the power 0, which is nothing but 1, right? Now coming to the this Twiddle factor itself, so I will give you a very easy way how you can calculate these values. So if you look into this Twiddle factor, it is nothing but we are having one angle of minus 2 pi by n. Okay. Now if you break this down, it is basically e to the power minus j theta. It is in this form. So this is nothing but equals to cos theta minus of j sin theta. Now if you try to find out the modulus of this one, we get cos square theta plus sin square theta, which is equal to 1. Okay. Now what is this? This indicates that we are having a unit circle. We are having a unit circle, which is basically unit circle means the circle it is having a radius of 1. Okay, and if you see it is in the complex domain, because this is a complex exponential component, so it will be a complex one. So the real axis, the x-axis, it will be a real axis, and the y-axis it will be an imaginary axis. Okay, if you see, this is nothing but an equation for a circle, and this circle is basically a unit circle, in fact. Okay, now if you see this unit circle, it starts from 0 and it moves down and it comes back to again 0, which is basically the 2 pi. Now if you see over here, if I have to calculate the Twiddle factor matrix for say W2, so our n is 0, 1, 0, 1. So if you see, first we will be having W2, W02, W02, W02 and W12. And if you look over here, what we are saying, we are having a factor e to the power minus j 2 pi by n. If we consider this 2 pi by n over here, so let me take this black here. So 2 pi by n, and if we replace this n by 2, so 2 pi is 360 degree and divided by 2, it comes out to be 180. So the points would be 180 degree apart, and we will take 0, this point, as the first point, and the next point would be 180 degree apart. That means it should be at pi. And since we are having this negative value, we will be going in a clockwise direction. Otherwise, what is the convention? We go to 0 to pi and then pi to 2 pi. But since we are having this negative this value over here, we will go in the clockwise direction and not in the usual anti-clockwise direction. Okay. So W0 is this point. What is the value? If you see, it is having a value of 1, 1, 1, and W12, it is at pi. What is the amplitude of this at this point? The amplitude is -1, right? So we get W kn2 as 1, 1, 1, -1. Similarly, if we have if you have to calculate the 4-point Twiddle factor, it will be WNK4. So we will be having, say, 0, 1, 2, 3, 0, 1, 2, 3. So W0 is W0, 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 1, 2, 3, because 1 multiplied by 0, 1 multiplied by 1, 1, 1 multiplied by 2, 2, 1 multiplied by 3, 3, and so on. So we make this matrix, and then our 360 by 4, it is nothing but 90 degree. So we have same. We will start with 0 over here, 90 degree apart, 0, 90, then again 90 this point, then again 90 this point. So let's mark it 0, 1, 2, 3. But we have seen that the frequency component, it is repeating itself. So after 3, we will be having 4, 5, 6, 7, 8, 9, and if you see, we have values up to W9, 4. So we will just put up the values from here. W0 is having a value of 1, W1 is minus of j, W W0, 1, 2, 2 is minus 1, sorry. Then W3 is j. Then again W4, it will be having a value of 1, and so on. So we have just, if you see, we have just put the values of this W and K over here. And this, believe me, this is the simplest way to find out the Twiddle factor matrix. Okay. Otherwise, you have to go for a very long calculation with all of this. Similarly, we can go for we can calculate WNK6. First, make the matrix values, say 0, 1, 2, 3, 4, 5. Similarly, 0, 1, 2, 3, 4, 5, and so on. And then 360 by 6. So 60 degree apart, 0, then 60 degree apart, from here 60 degree apart, from here 60 degree apart, it will be coming at this pi, right? Then from here 60 degree apart, and then again 60 degree apart over here. So you will be having 6 values, 1, 2, 3, 4, 5, and 6, and their values will be the first one 0.5 minus j of 0.866. So in this method, if you do it, you just have to find out one coordinate, and the other coordinates, only the positive and the negative values, they changes. So these two values they are conjugate of themselves, and these two values, they are also conjugate of themselves. And similarly across the y-axis also, we can just have the change in the signs, and we can get the thing. So if you get only one value, you will be able to calculate all the values in a really quick fashion. Otherwise, if you go by the formula, you have to calculate all the values. Okay. Now, yeah, this is a very interesting thing, or a interesting numerical, which I always want my students to know. So what is it? It says xn equals to 2 of 0. So basically, if we consider this signal, it is nothing but x of n only 2. Okay. We have to remember that when we are doing the DFT can only be done on even even length. Even length signals. That means 2 point, 4 point, 6 point and 8 point DFT can be done, but 1 point DFT cannot be done. So in this case, if we have xn equals to 2, so we have to convert this signal into 2 point signal, which is 2 0, and this addition of the 0 at the end, it is called zero padding. Okay, so you want to perform 2 point DFT. This is our 2 point Twiddle factor matrix multiplied by this signal component 2 0. So this is a 2 by 2 matrix and this is a 2 by 1 matrix. So what will be the resultant length of the signal or the resultant matrix? It will be 2 initial one by the later one of the next one. Okay, so it will be a 2 by 1 matrix. So we get a 2 by 1 matrix. So xk we get 2 comma 2. Okay, and if we go for the IDFT, so 1 by 2 multiplied by this should be a conjugate Twiddle factor matrix. Okay, it should be conjugate Twiddle factor matrix. But when we are talking about the Twiddle factor matrix for 2 point DFT, the conjugate Twiddle factor matrix and the Twiddle factor matrix, they are for a 2 point DFT, they are same because there are no complex numbers over here. Okay, so 1 by 2 multiplied by the total 1 by 2 y 2, this is basically the 1 by n, so that's why 2. Then we have the conjugate Twiddle factor matrix multiplied by x of k. So when we solve this, we get 2 0, which is nothing but our xn. Okay, similarly if we go for xn 2 comma 0 0 0, okay, then again we find out the xk, we do all the calculation and we get 4 numbers. Instead of 2 numbers we get 4 numbers. Okay, now again if we do perform the inverse transform, herein we will be getting the original signal, this thing. Okay, now if you compare this Twiddle factor matrix and its conjugate W4nk, and here WNK conjugate for all the complex variables, they are having the opposite signs. Okay, so see, all of them, they are having opposite signs. Okay, so if you calculate the normal Twiddle factor matrix, you can easily calculate the conjugate one, and you can use it easily for the IDFT purpose. Okay, now over here, one of the important thing what you need to understand is that while converting it to the this 4-point DFT, what we have done over here is basically we have increased the signal length. So you are getting a whole lot of point. So for the same signal, at the initial stage you are getting 2 points when you are doing it for the 2-point DFT, and when you are doing the 4-point DFT you are getting 4 points. So what does that means? This means, suppose there is a scenery say one object is there, okay, on one side, and on the other side you are standing, and in between you are having a blocked window. Now in this blocked window, suppose I create a window, transparent window, I strip off certain part of this thing at two places. So what you will be able to do, see, you will be able to see the part of this object. This object is already present, okay? This object is already present, but you will be able to see some parts of the signal, okay? Now, when you further increase, suppose initially it was only when we are having the green portion, it was 2 point DFT. So you are able to see only certain parts. Now again, when you added this what you call maroon windows also, it became 4 point DFT, right? So what happens now? As comparison, in comparison to the previous instance, you are able to see a more clear picture of the object over here, right? So as you go on increasing the number of points in the DFT, you will be able to look into the other side object in a more clear picture, okay? So you will say, sir, if I have a corrupted signal, and if we increase the 8 point DF, if we increase the signal length, it should be able to help us in getting a better resolution. No, if a signal is corrupted, say while you are what do you call, while you are doing the sampling, if you do not take the proper care and the signal is already aliased, that means the signal is already giving you a very crappy result or crappy information, then even if you increase the signal length, you will be able to look into the frequency components with a better resolution, but that information will also be not a good information or a good quality information, okay? So whenever you have to get a signal, when you want to convert discretize a signal, you have to take care that there is no aliasing in the signal. However, if your signal is a good quality signal, and then by zero padding you are increasing the signal length, then it can help you in observing the frequency spectrum in a more with a high resolution power, okay, with a higher resolution. So if you have a higher signal length, you will be getting a higher resolution, okay? So that's it. So I have another example, but today I don't think we will be having time. So today we will stop over here. In the next class we will be discussing the next one. Any questions? Do you guys have any questions?
No, sir.